Hi, this is Yogesh Langi, and in this video we will learn a numerical on two different layers of insulation. So on the screen the sequence is given: a steam flowing through a long thin wall pipe maintains the pipe wall at a uniform temperature of 500 Kelvin. The pipe is covered with the insulation blanket comprised of two different materials A and B. The interface between the two materials may be assumed to have an infinite contact resistance, and the entire outer surface is exposed to air, for which the T infinity, the outer temperature 300 Kelvin, and the H heat transfer coefficient is 25 watt meter square Kelvin. What is the total heat loss from the pipe for a prescribed condition? So here it is given a diagram, and the statement is clear that it is a pipe with a uniform temperature of 500 Kelvin inside the pipe. So steam is flowing with the pipe, and there is a two materials which are wrapped on the pipe. So material A, this one, and material B, this one, with a different conductivity. The conductivity of material A is the conductivity of material A is given 2 watt, and the conductivity of material B is given 0.25. With this one, they say that here is the one section, a half section is wrapped by material A. So if we say this section is wrapped by material A, and this one is insulated by material B. So we want to know what is the total heat loss. What is the total heat loss from this condition? The other dimensions are given. The inner diameter of a pipe is this one. It is 50 millimeter. Outer diameter of insulating one, it is 100 millimeter, and the surrounding temperature is given 500. So here they asked the two things. The one thing is what is the total heat loss from the pipe, and another is what is the temperature at a surface. So what is the temperature here and here one. So here it is clear that there is a heat transfer through this one, through the pipe, and we want to know what is the heat loss from this pipe. So let's start to how to get this answer from this statement. And as I described that this diagram, so the heat loss is one. The heat loss is from this surface, this one, okay, and another is by this surface. So let's see how to solve this one and to get the total heat loss from this one. So here first we are assuming the things. So what we have assumed, we assume the steady state condition, because on that one we will work on. So assume a steady state condition. So this is a very important one, to assume steady state. So here we are assuming that heat is transferred through the pipe is on steady state. Okay, and the second assumption is that it is a one dimensional one. It is a one dimensional, and the heat is flow through in a radial direction. It is flow in a radial direction. So heat is flow in the radial direction. So that is the assumptions. Now first we will start this particular numerical, as we have two different layers here, the layer A and layer the insulation 1A and insulation B. So first what we do, we just make a thermal circuit. So just draw first a thermal circuit for it. So from the diagram we can draw a thermal circuit. So how to draw the thermal circuit? So if you see from this diagram, then you can see the heat is transferred from this surface, okay, to this insulation material, and from this insulation material it is transferred to the atmosphere. Okay, the one is heat is transferred from this surface, from the inner one to this insulation, and from the insulation surface to the surrounding. So obviously the heat is, there are two resistances here. One resistance is by this material of insulation, and the one resistance is by surrounding. So we can have here the two resistances, the conduction resistances here and the convection resistances from here. Similarly, so this is the one thing. Now as we say that this is a half surface is covered by the material, same way it is happened here from this surface. Okay, so from this steam to this heat is transferred to this insulating material B, and from the surface B to the surrounding. So here also there is a two resistances, the one resistance conduction and convection. So this is for a material A and for material A. So similarly, a conduction from material B means from here, and a convection. So there are the four resistances are here. So let's draw a diagram for it, and from that one we can easy to work out and to get the answer of it. So here, as I said from that diagram, so let's say that the first resistance, so this is the first resistance, I draw it, okay, and there is intermediate temperature. So here this is a R conduction by material A, and then again I can have another resistance, okay. Here this resistance is by R convection one, so we write R convection and the material is A. Similarly, I can draw here. Why I am drawing here? If you see, this is in a series. So first heat is transferred to the insulating material, and from the surface of insulating material to the surrounding. So conduction in the insulating material and convection. Similarly, these are the parallel one. Which one parallel? If I say here, so if you see on this surface, okay, on this one, a half surface, I just want to show you here, okay. Say, so this one, this surface, okay, first, so it is a conduction one, and from this one convection part. And similarly also in the next section, this one is again a conduction, and then there is a convection part. So let's simplify this one. So we draw the diagram accordingly, and we write that as, so this is R conduction but for material B, and similarly here is the temperature, and here is again R convection for material B, and then a total heat is transferred from here, okay. So here we say this is a temperature T, okay, T temperature of steam, and this is temperature of surrounding. In between we have the two temperatures, the one temperature at this point between these two junctions, because we have such type of the diagram, okay. And if you see, then the first part is this one, so at this one, okay. So this is the things here. So we can, if I want to connect, I can connect like this one, okay. So and the convection one on the surface one, and similarly for the next part for the B. So once we draw the diagram, we will see that there are the four resistances are here, and the two resistances, this one and this one, are the series one, and then it is a parallel one. If you look here, then I can say that this and this one is by a series one, and this is series, but if we connect this one, then it is in a parallel way. Okay, and accordingly we are writing the equations. Now we are writing the equations in terms of resistances. So let's first write the for the R convection. So I can write for R convection A, which is equals to the R convection B. Why I'm writing this one is equals to the, because R convection A and R convection B, because on the surface of the insulating material, the convection term is there, and it is the same temperature. So on the basis of that one, I am writing, and the formula is 1 upon a pi resistance of radius of the outer one, and h is the heat transfer coefficient, and h. Okay, why I'm not taking this one, it is, if you see the resistance by the convection, we always to write or prepare 2 pi r h, but as we see here, we are using a half portion of it. Okay, so that's why I'm writing this is 1 upon I r2h. Similarly, I am writing for the r conduction. So for the r conduction material A, I am writing the equation as ln of r2, or outer radius, minus upon inner radius, upon it is pi, and the conductivity of a material A. So here I am writing just because I am considering the half area on which the heat is transferred, because here only we consider this half portion. Okay, we consider this half portion. Okay. Similarly, I am writing for R conduction for a material B, and again I can write a formula, that is the ln of R2 by R1 upon pi, and here the conductivity of material B. Okay, then we just put it the values what you have given in this numerical. So to calculate the R conduction of A, then I can have a formula, and we just put it the values. Ln of the R2 value is 0.1 after doing the conversion, and the R1 is value is 0.05, and upon the pi into, and the conductivity of the material A, I'm taking this one. Okay, the conductivity of material A is 2. So once I do the calculation, I got a value is around 1.1103. It is in meter Kelvin per watt. Okay, similarly I just have another term, it is R conduction B. So I can write for R conduction B, and for that one I can write a formula, and I just put it the values of R2 and R1. So here the value of R2 is 0.1, R1 is 0.05, okay, upon it is pi into, I am just taking the conductivity of the material B, and the conductivity of material B is of 0.25. So here 0.25. So once I do the calculation and I get a value. It is 0.8825 and the unit is meter Kelvin per watt. Okay. Similarly, I have to just do the calculation for R convection A and R convection B, which are the same value, and here I can write the formula for that to calculate. It is again for R convection A and for the R convection B. I just put it the values into the formula is pi into the value of R on which the heat is transferred 0.1 into the H. It is a heat transfer coefficient that is given 25, and yes, from that one we can get a value of R convection A and B is around a point. I get a value is 0.1273, and yes, the unit is again a meter Kelvin per watt. Okay, so now I get a value of all the R conduction A, then I get a value of R conduction B, I get a value of R convection A as well as B. Okay, now I just use the equation, and from that one I can get a value of total heat loss from the pipe, and for that one I just use to first calculate how much heat is transferred on the surface A. It means I just want to know, if I see this is the diagram, one second. If we look this diagram, then first I try to get how much heat is lost from this section, from the section A. It means how much heat is lost from this surface. Okay, only I am considering this portion. I'm just considering this portion. Okay, and for that one I just want to know how much heat is lost from this material, and then I will go with the another one. So let's first write the equation for heat loss through this section. So heat loss through this section, we can have a unit, we can have a formula for that one. So for the first case I am writing the formula for heat loss. It is heat loss from the insulating material A, and I can write a formula which is, it is the temperature of steam which is flow inside minus a temperature of the surrounding upon, it is R conduction A and plus R convection A, because from this section the one heat is the one resistance is by conduction and the one resistance is by convection. So that's why I'm taking R conduction A plus R convection B, that is the total one. So R conduction A plus R convection A. So I just put it the values of it. So from that one it is TS value is 500 minus T infinity value is 300, which is mentioned, upon R conduction value which we calculate, and the value of R conduction A is 0.1103, and from a resistance of convection it is 0.1273, and so we get answer, it is Q of A, which is the 842 watt per meter. So this is the first section where the heat is lost from the insulating material A. Now what happened on the insulating material B? So on the insulating material B, how much heat is lost? Then again we use the same formula, only the small change that we have. So we can write a formula for the heat loss from the section B, that we say B means from the insulating material B, which is again I can write, it is the heat the temperature of a steam minus temperature of a surrounding upon R conduction P plus R convection B. So by just putting the values of all these one, I got a value of is. So I just put it the values 500 minus 300 upon, I can write what I calculate in the R conduction. For the B it is 0.8825, and yes, for R convection B, which is again it is 1.273, and so we got a value of the heat loss from the B section, which is around 198. So we can say that here the one heat losses from section A and section B. So if you see the heat transfer rate, so total heat loss or heat transfer rate, so we can write a total heat transfer is, it is QT, we can represent it is Q total, which is equals to the heat loss from section A and heat loss from the section B. So once we do the addition of this one, then we can get a value which we can say it is 842 for the A plus 198 for the B, and so we got a value is 1040 is the watt per meter. Okay, so this is the heat loss from it. So total heat loss is, we can write it is 1040. So this is the final answer, that how much heat loss or how much heat that you predict to losses from the pipe. Now if you want to calculate what is the temperature at this point at the surface of insulation for material A and for material B, then we again to calculate these things, and yes, it is very easy to calculate. Just we have to write formula for that one. So if the question is what is calculate the heat sorry, calculate the temperature at the surface, at the surface. So we can write a simple formula for that one. So what is the temperature at this point inside this surface, and what is the temperature at this surface? So for that one, for the case 1, just consider the case 1, which we take a material A, and so we can have a formula for that one. Heat transfer through the section A is equals to the temperature of steam minus a surface temperature, which we consider is T as 2, and for the material A, okay, upon it is R conduction A. So we take a resistance, it is R conduction A, because we say that the heat is transferred from this surface to this one. As we have a we know the temperature here it is 500, we know the surrounding temperature is 500, but we don't know what 300, but we don't know what is at this point, and for that one we use this formula. So value of Q that we know for the QA, which we calculate already, it is 842. Ts temperature that we know, that temperature of the steam which is going through the pipe 500 minus Ts2 for a surface A that we want to calculate, which we don't know, we need to calculate that part, and upon it is the R conduction, and for the R conduction value is 1103. So from that one we can easily get a value of the surface temperature on material A, and we got a value is around 407 Kelvin. Similarly we can do for the second part for the B, for this part, what is section in this one. So again we can write a formula, heat transfer rate to the B, which is equals to the surface steam temperature minus surface temperature or surface the material B upon I can take it is R conduction B, because we consider here the B. Okay, we need to calculate that part. So QB, that we know what is the value of QB, and here again a QB value is 198, which already we calculate. A TS value is given 500, same temperature. This we need to calculate what exactly the temperature of on this surface of B material. Upon we can write it is R conduction B, and the value of R conduction B is of 0.8825, 0.8825. So once you do this calculation, you will get a value of surface temperature, okay, at section B, which we get a value is 325 Kelvin. So you can see here how the temperature, when there is a material A, we got it is 407 is the temperature, but here we can reduce a temperature of 325. It means if you see the conductivity of the material B, which is 0.25, and conductivity of material A is 2, it means from this one we can easily say that we can have a less heat loss if I put a material B on a whole coil. So this is numerical, and from that one we calculate a total heat transfer through this section and the surface temperatures. Thank you.